Okay, so I want to make sure you can see what's on my screen. So you should see transformations of trigonometric function 6.4. I'm just going to move it actually a little bit up. Just want to make sure you can still see all of this because I want as much room as possible for my graphing. Okay, so hopefully you can see all of that. If I can get someone to verify. Yeah, Arnold, I got the recording going. Okay, so we're going to start with transformations of trig functions. The first thing I wanted you to look at over on the left-hand side is we're really only going to talk about graphing and transforming the primary trig functions of sine and cos. But keep in mind, all the transformations that we've done so far earlier on in the course, the same properties still apply. So if you thought you were getting away from transformations, unfortunately, no. We can transform any type of function, and that's what we're going to look at today. So the regular sine function, if you remember, has these points 0, 0, pi by 2, 1, pi 0, 3 pi by 2, negative 1, and 2 pi 0. And the way that looks, remember, is a nice looking sine wave. I'm just going to draw in my axes very quickly. And why am I not able to get the drawing feature? Oh boy, something happened. Folks, I'm scared. Something's going on here. Give me a second. Ah, there we go. What's going on? Okay, so basically we've got these different points here. Okay, that would be negative pi by 2. It's negative pi. This would be pi by 2 and then pi. And then this would go 1 and negative 1. And obviously this isn't going to be very good to scale, but I'll try to make it a little bit better. Okay, so I think that should be like that. Okay, so the first thing is from 0, 0. I guess I went into the negatives, but 0, 0 here, then at pi by 2 goes up to 1. At pi, it goes down back to 0. At 3 pi by 2, it goes down to negative 1. And then at 2 pi, it goes back up to 0. Now it follows this exact same pattern in the negative direction as well. So at negative pi by 2, it would go down to negative 1. And at negative pi, it would go back up to 0. And it basically just continues on with this curve. Okay. So that's what the regular sine function looks like. But if we were tasked now to graph this, so to graph y equals 3 sine 2x plus pi by 6 minus 1, then we should be able to do that no problem now, right? So this should actually be a very quick piece because we know how to do transformations. So I just want a quick help here. There are a few things that help us, or I guess I can't write in pi by 6. So what do these values do for us? What does the 3 do for us in this case? I want to know what the 3, the 2, the pi by 6, and the negative 1, what do they do for us? What are they going to do to the original sine function?
The 3 changes the amplitude. It's a horizontal stretch.
Okay. Okay, yep. So you're absolutely correct. So the 3 is a vertical stretch, which what that will do is modify the well, I guess it acts on the amplitude. Okay. What about the 2? What does the 2 do?
Isn't that a horizontal compression?
Yep. So this is a horizontal compression. And so what does that actually, what does that change? Does it change the amplitude? That is going to change. Okay, Christian says it's going to change the period, which that is correct, right? So that's going to change the period. What's the pi by 6 going to do?
Shifted pi by 6 to the left.
Yep, so in this case, it's going to be a horizontal shift left pi by 6. And then the minus 1 is going to do what? So I see Christian says it's going to go up, but it's minus 1, so this is not going to go up. So Zainab says it's going to shift up or down. You are correct. So this is going to be a vertical shift, and it's going to be down 1. Okay? Now, that's the initial piece that I want you to think about there. It's because we have these values, and we should already know what they do. So this actually becomes no more than what we did in the first unit, where we were just using function mapping in order to transpose those points into different spots, right? Now, the only difficulty with this is that it makes it so that we're not going to get the nicest of numbers, okay? But what we're going to have to do is look and see, well, what do we take from our old function, like xy, maps to become what? Okay, so from our old function, this y equals sine x, these points in the table of values over here that are x and y, what do they map to? So we've got to figure out how we can figure out what the x's are and what the y's are. So remember, we've just identified what the horizontal and vertical are. So the horizontal, this one, and the vertical, this one, are going to, the horizontal there and there. We've got to figure out what to do. So the first thing we're going to do here is we are going to do our stretches or compressions before our shifts. So because this is a horizontal compression, we are going to say it's a horizontal stretch by a factor of 1/2, or it's a horizontal compression by a factor of 2. So we would say we would take x, divide it by 2, and then we are going to, since it's going left, we are going to subtract pi by 6. Okay, hopefully everyone's in agreement with that. Right, and then in the y, what we're going to do is because it's a vertical stretch, and then it's shifting down, it's a vertical stretch by a factor of 3, so we're going to multiply by 3, and then we are going to subtract 1. Right, so what you'll notice in the sine wave here is that the y values are not going to be that difficult to transform, but the x values might be slightly difficult to transform. Okay, so that's what we're going to look at doing here. Okay, so if you guys can help me out with a new table of values, I would appreciate it. So I'm just going to draw that over here. So really, this I'm going to call x prime and y prime because that's our new piece. So I'm just going to call this point like xy prime, right, or the image. So x over 2 negative pi by, or minus pi by 6. So the first one becomes pretty easy, right, because we would be taking the point 0, 0. So if we put in 0, 0 for our first point, we get 0 over 2, which is 0, and we get negative pi by 6. And then 3 times 0 minus 1 becomes negative 1. Okay, so all I'm doing, I'm taking these values here for x, and I'm subbing them in right there. Taking these values for y, and I'm subbing them in right here. Okay. So what I'm actually going to do, I'm just going to do all the y's first because it's going to make the most sense for me. So if I put in 1, I get 3 times 1, which is 3, minus 1, I get 2. If I put in 0, I get negative 1 again. Then I'm going to go down to negative 2 because 3 times negative, sorry, not negative 2, negative 4. 3 times negative 1 is negative 3, minus 1 gives me negative 4. And then 0, I end up getting negative 1 again. Okay, but now the x values, so I've got to divide pi by 2 here by 2, which is now pi by 4. And then it's pi by 4 minus pi by 6. So pi by 4 minus pi by 6 is going to give us, if we put that out of 24, or sorry, we put it out of 12, it's 3 pi by 12 minus 2 pi by 12, so you get pi by 12. Okay. Did I do that one correctly? I hope so. Okay, the next x value, we've got pi. So now we're going to take pi divided by 2, and then minus pi by 6. So that one shouldn't be too difficult. We get 3 pi by 6 minus pi by 6, which is 2 pi by 6, which is equal to pi by 3. Okay, so then our next point here is pi by 3. Next one is 3 pi by 2. So we divide that by 2, which is 3 pi by 4 minus pi by 6. Again, we're going to make that out of 12. So 9 pi minus 2, we get 7 pi by 12. And then finally, we are at our last one, which is 2 pi. 2 pi, we divide by 2, and then subtract pi by 6. So that's just pi minus pi by 6, which is 5 pi by 6. Okay, so really what we've now done is we've generated these different points, or our function mapping points, which are negative pi by 6, negative 1, pi by 12, 2, pi by 3, negative 1, 7 pi by 12, negative 4, 5 pi by 6, negative 1. Now, those numbers may look very weird to you, and I'm assuming they do, right? So I'm assuming you probably don't see much benefit to looking at these numbers. But what I actually want to show you is that these numbers actually, they make a lot of sense if we write them all as the common denominator of 12. Okay, so I'm just going to erase these very quick, or I'm going to erase this part very quickly. It's supposed to be very quickly, but it's not going very quickly. Okay, so what these points turn out to be, if you write them all as a common denominator of 12, would be, it'd be negative 2 pi by 12, negative 1. Pi by 12. You know what? I'm not actually going to show the points in there. I'm just going to show what those values would be. So let me get a different color. Okay, so this would actually be negative 2 pi by 12. This is 1 pi by 12. This is 4 pi by 12. 7 pi by 12. 10 pi by 12. Do you notice what the pattern is here? Every single time you're increasing by 3 pi by 12, or what you're doing is you're increasing by pi by 4. Okay, so really that's nice, because what we can then see is if we know what we're changing by each time, then we should be able to see that same pattern between every single one of these points in terms of the x values, which should make sense because the original points we started with, they had a common difference in terms of how spaced out they were. It's not like we were choosing one thing that was at 30 degrees and then one at 90. No, we chose 0, 90, 180, 270, 360. So if those are all spaced out equally, then our mapped points should also space out equally. Okay? So now let's try to graph this thing though. So we've got some nasty looking things, right? But keep in mind here, we're going from negative pi by 6, which that's really like a negative 30 degree angle if you want to convert it. Then we're going all the way to pi by 12. So pi by 12, if you think about it, is half of pi by 6. Pi by 6 is a 30 degree angle, so this would be a 15 degree angle. Then pi by 3 is 60 degrees. So what you're really seeing is we're increasing by 45 degrees every single time. Now that might help you with your diagrams here. So this, remember, is negative 90 degrees. So if we're looking to graph our first point at negative 30 degrees or negative pi by 6, that's probably somewhere like right here, right? So that's probably negative pi by 6, and then that starts at negative 1. So that's our first point, okay? Hopefully everyone can understand that. Now then we're going to go to positive pi by 12 or 15 degrees. So that's going to be like here, something like that. But then we're going to go all the way up to positive 2. Oh boy. Right, so at this point here, we're going to go all the way up to positive 2. Then it says we're going to come back down to negative 1 at pi by 3, which is at 60 degrees, which is probably somewhere around here, right? Okay. This is looking weirder and weirder. Now we're going to 7 pi by 12, which is just over 6 pi by 12, which is, so it should be just past pi by 2. Okay, it'd be 105 degrees. So it's going to be something like here. It says we go all the way down to negative 4. So this way down here would be negative 4 and something like that. Again, remember this is not fully to scale, so I apologize. And then it says we go back up to 5 pi by 6, negative 1. So 5 pi by 6 is almost 1 pi, but it's 30 degrees less. So that's actually like 120 degree angle, or sorry, 150 degree angle. So probably something like there. So then we get that last point. Okay. And now what we're tasked with is drawing the graph. So we're connect dots time. I'm actually just going to use a highlighter here. So give me a moment. Okay. So we're going to start here. We're going to go all the way up to that point, come back down through there, and that was ugly. So I'm going to try that again. Dang it, I did the exact same thing that time. One more time. Oh, that's pretty. Almost. Okay, so basically what I've done is I've taken that first function. Okay, now keep in mind, I only have taken this portion of the function though. So I've only started with these points here, and that turned into this new function that I just graphed. Okay, so this point here, if we look at, give me a second. So this point right here at 0, 0 turned into this point here, right? That's a stretch, a compression, a shift left, and a shift down. This point here was stretched vertically, was compressed horizontally, was moved left again then, and then shifted down. Okay, this point here, stretched, compressed, shifted left, shifted down to this point. This point here becomes that point there becomes that point. Okay, so are there any questions on that before we go down or before we go on? I'm assuming there probably are, but if there's not, then that's awesome, because then that means everyone is either sleeping or everyone understands exactly what we're doing. So I'm going to give it a quick second before I move on. Okay, so I'm assuming that everyone's good with that. So I'm just going to go into, one person. Sir. Yes, I am, sir. Okay, I'll wait for your question, but I'm going to move on. Would you rather do it in radians? Yeah, I am doing it in radians. So yes, I would prefer you to do this all in radians, but that's not to say that you can't convert it back to degrees for just to help you out. Okay, so like when I do pi by 6, I'm always going to think, okay, what is pi by 6? It's 30 degrees. Okay, so I know where it is, but I don't have to. I'm not going to graph it on my scale as 30 degrees. On a test, when I give you the scale, when I ask you to graph this, the scale will already be there, and it will already have pi radians on it. Okay. All right, I just want to show you quickly that that is correct. So I'm just going to switch over to here. Can you guys all see Desmos? Someone give me a shout if you can. Yes, no?
Yes.
Okay, thank you. So I want to be in radians. I want to be in from what? Go -1 to 7. Sure. Okay, so that's the regular sine wave that we just kind of graphed. So the original one, so that's at 0, 0, pi by 2, 1, pi 0, 3 pi by 2, -1, and 2 pi 0. So I'm just going to put in the rest of that. So y is equal to 3 bracket, what was it? 3 sine, 3 sine 2x plus pi by 6 and then all minus 1. Okay, so let's look at those points again. Wait a second. Okay, so you can see here that 7 pi by 12, -4, the pi by 12, 2, right? Those were points that that we had for here and here. Now at the axis, I want to say that's going to be, it doesn't give us the exact value for that. Oh well. That's okay though. I wish it would. Okay, so one thing I do want to I want you to notice back here on our graph is that the axis here and the amplitude have changed. Okay, so hopefully you do see that. The axis here and the amplitude have definitely changed. Now, if you remember, we were defining the axis and amplitude last week in class. We had said that the axis was kind of what goes right through the center here. Okay, so in terms of our axis has actually been shifted down 1. Interesting, right? So where do you get the down 1 coming from in our equation? Anyone know where we get the down 1 from? Yes, no?
Value.
I'm sorry?
The C value, the -1 at the end.
Yeah, so the -1 at the end. So this actually moves our axis down. Okay, so that -1 impacts where our axis is. So that basically helps us to understand that, okay, if that's -1 up there in the top, like as this value right here, then that means all the points where this was 0, so 0, 0, 0, that's now going to be -1, -1, -1, right? That's actually pretty nice to help us with that. And then if you look at the amplitude, so the amplitude, if you remember, we said you can calculate by going the max minus the min divided by 2. So the max minus the min is 2 minus -4, which is 6. 6 divided by 2. Our amplitude is 3. So notice here that vertical stretch, right? The amplitude is actually whatever that value is as our A value. Okay, so it's just some interesting points to note. And I know we've kind of already done that, but the 3 here is our amplitude. Okay. The -1 here is our axis. Okay, so that can drastically help us out when we want to try and figure out, okay, well, what is this thing going to look like? So we can use the amplitude, we can use the axis to help us figure out, do our numbers actually make sense? All right. So if everyone's okay with that, I'd like to move on. I'll do give me a second. What do I need to do here? What was I going to do? Save. There we go. Okay. So one other thing I want to do And this is just another example. Same type of a function, but this is an example using like heights. So if I said that h at t here equals 10 times the sine of 2 pi t plus 1.5 pi plus 15. Okay, then, I mean, we could graph the exact same thing here, but notice we want to get this into that format like we used to have, where there's a k value that's kind of factored out here. Remember, we want this to be like the sine of k x minus c, right? If you remember that, we have to factor that out first. So inside here, we have to factor out whatever, in this case, it's going to be the variable of t, not of x. But we're going to have to factor that out first. So I'm just going to do that really quickly. So it's 10 times the sine of, we can factor out a 2 pi here. Right, so if we factor out a 2 pi, then we're going to be left with t plus, really it's 1.5 pi over 2 pi plus 15. And if we do that, really 1.5 over 2 is going to give us 3/4. Right, so simplifying it again, 10 sine 2 pi t plus 0.75 plus 15. So in this, notice we're not really looking at this as being a, I guess when we talk about it, this, or when we look at this, this equation, this is not actually a function of the angle anymore. What we're really saying is this is like height and time. Okay, so we would be graphing this on a height versus time axis, and the shift isn't going to be in terms of pi radians anymore. It's going to be in terms of 0.75. So we're not dealing with pi radians anymore. We're dealing with just radians. Okay, so in this case, we would take our regular points here, and we could do all the shifts and stretches and everything like that. But all I really wanted to show you in this case was that if you don't have that k factored out, you need to make sure that you factor it out and get it to be like this. Otherwise, you're going to run into some serious issues. Okay. Now, one thing, we can graph this if you want. Remember, so we can just take all of our points. So 0, 0, pi by 2, 1. Pi 0, pi by 2 negative 1, and then, sorry, that should be 3 pi by 2 negative 1, and then 2 pi 0. And we can do all of this fun stuff, which if we're analyzing this, we would say that's horizontal, sorry, that's horizontal and that's horizontal. So we would basically then say that this is going to go, x is going to map to give x over 2 pi, and then since it's moving left, it would be minus 0.75. Okay, and then y here, do it a different color. So y here would map to be 10y plus 15. Okay, so we do that with every single one of those values. Okay, I'm going to do the y's first because they're always easier. So 10 times 0 plus 15 is 15. And look at that. Those will be all those three. 10 times 1 is 10 plus 15 is 25. 10 times negative 1 is negative 10 plus 5 is just 5. Right? And so now we can look at the x's, and the x's won't be too difficult either. So we'd be saying, okay, 0 divided by 2 pi is 0, minus 0.75 is negative 0.75. Pi by 2 divided by 2 pi is just, let me check. Pi by 2 divided by 2 pi, you end up getting just 1 over 4. Right, so you get 1 over 4 minus 3/4, which is 0.75. So you'd get negative 1/2 or negative 0.5. And keep doing that. So here, pi. So we get pi by 2 pi minus 0.75. And that'd be 1/2 minus 3/4, which is negative 1/4. You guys get the point here, right? Now notice you can probably see the progression here. Negative 0.75 to 0.5 to 0.25. You're going down by you're increasing by 0.25 each time. So this should give us a 0. And then this should give us positive 0.25. Okay, and if you don't want to believe that, then that's okay. But yeah, so basically that's what we end up getting, and then you can kind of just graph those on a regular graph. Okay, so I'm not going to do it, but you'll end up seeing here that like, oh, look at that. That's actually a very horrible diagram. But the things you should know about this is that your axis will be at y equals 15. Your amplitude will be 10. So basically, from that graph, if you're starting here, you should be at like 15, and then that's going to be your axis. And then regardless of where, like which way you're going to go up to and then down to 5 and 25. So I'll do something like this, depending on whatever your period is. Okay. So yeah, Christian's saying the functions are periodic. Absolutely they are, because they just keep going on and on and on and on and on and on and on, and they're going to repeat themselves with a period. So the interesting thing is that you can tell what the period is, and the period is always going to be 2 pi divided by whatever this k value is. So it's going to be 2 pi divided by k, where whatever you factor out is going to be the k value. Okay, so like right here, this is your k value. Okay, so when we do this, x divided by 2 pi, the reason why we're doing that is because we're dividing by the k value, and that is going to give us whatever our period is. So our period here is going to be 1. So from start to finish, that's going to be 1. And another one here, it's going to be 2, 3. And it should make sense, actually, if we're looking at one period starts at negative 0.75 and goes all the way so that's 0.25, 0.25, 0.25, 0.25. That's from negative 0.75 to 0.25. You've actually gone one period, and you've really only gone from negative 0.75 all the way to positive 0.25, which is 1. Okay, so your period here is equal to 1. Okay, any questions? So using that, then you can kind of get into, I mean, you can do the exact same thing with the cosine wave, except the cos wave doesn't start with those same points, right? It doesn't start with 0, 0, pi by 2, 1, pi 0, and that. The cosine wave starts with something different. So cos starts at 0, 1, pi by 2, 0, pi negative 1, 3 pi by 2, 0, and 2 pi 1. So you just need to know your initial points, and then all you're going to do is the exact same thing. Function mapping, you get your new x's, you get your new x's, you get your new y's, and then you graph it. But the same thing is true about the axis, the same thing is true about the amplitude, the same thing is true about the period. Okay, and so really that's what you need to know in order to graph sine and cos transformations. All right, so it's I don't think it's that bad, but if you don't, I mean, if you don't know how to graph the regular transformations, then it's difficult. B, if you don't remember how to draw the sine and cos wave or sine and cos function, then it's also difficult. Okay. Now, where does so we're going to go into this next little part, which is basically where are the applications. So I know Arnold was asking me, when does that ever come into play? So he got when sine and cos came into play. He asked where tan came into play. So with sine and cos, it's a lot easier to look at, but the classic example is always looking at something like a Ferris wheel. Okay, so let's look at this Ferris wheel problem. So let's say we want to model a Ferris wheel motion in terms of the height above ground and the time, let's say. Okay, so here's the idea of a Ferris wheel. You have you've got this wheel, obviously. Can I draw a circle in here? Need to see. Yeah, let me draw a circle. So you've got this circle, and basically what you do is you get on at a certain height, and then you ride around this fun ride that really does nothing in terms of excitement, but maybe you get to see some fun sights. I don't know. Okay, so basically, all right, there's all your little Ferris wheel people. People would be in these things if you've never been on a Ferris wheel before. But basically what you end up having is you have this circle and it rotates around in a certain direction. It really doesn't matter which direction. And you get back down to the bottom. So the interesting thing is that this will model a sine wave. And the reason being, you start at this height, and then as it rotates, you reach this height. And then as it rotates more, you reach that height. And then you come back down to this height. And then you go back down to this height. And you go up. And then you go to the max. And then you go to the middle. And then the bottom. And then and then the middle. Then the top. Then the middle. And the bottom. And the whole thing goes on and on and on and on and on. So there's some parameters around this that you'll need to understand. So what you can kind of do is you can, I guess we can really just model this by saying, let's say this is a 16 meter diameter Ferris wheel. And I'm not going to write out the full word problem-ish thing. I'm just going to give you the information that you need in order to do this. So it's a 16 meter diameter wheel. And what I'll say is that you enter the wheel at 1.5 meters above ground. Okay, because keep in mind, you're not starting on the ground as on the Ferris wheel. Sometimes you're starting maybe a meter above the ground. We'll say it's on a platform, which is 1.5 meters above the actual ground. Okay, and we will say that it takes 30 seconds per revolution. Okay, so that really is the only information you need in order to, first of all, graph this, and then second of all, in order to get the equation for it. All right, so who can help me out? Basically, we're looking for, what do you want to do first? You know what, we're not going to graph it first. We will look at, we're going to have to graph it while we're trying to do this, but we're going to try and get this. Y equals A times the sine of K X minus H plus C. Hopefully you're okay with those variables. So let's do that. Y equals A times the sine of K X minus H plus C. If you'd like, instead, you could use, instead of Y, you could use height above the ground, and K, you could use time, so just a T, but I don't want to confuse you with this H variable over here. So H is going to, so Y is going to represent the height, so the height above ground, and T is going to represent time in seconds. Okay, so can anyone help me right away with any of the values, A, K, X, or C? Because if we can figure out what A, K, X, or sorry, A, K, H, and C are, then we can get the what's it called? We can basically end up getting our value already, and then we're good to go. All right, so I'm seeing A is equal to 8. Giovanni says, Ashraf says C is 1.5. Christian says A is 16 over 2. Giovanni is C is 1.5. Okay, I agree with you both completely already. Period is 30 seconds. Okay, Ashraf's got a period of 30 seconds. And is there anything else that that'll help us? So I'm not sure we can identify the H right away, but let's start thinking about this. So everyone that's written something is right so far. So we're gonna look at why that is. Okay, so period is 30, altitude, or yeah, okay. Giovanni, I think you are almost close there. Oh no, sorry. Yeah, I think you're right. Okay, so let's look at this. So this is what I kind of want to do. So keep in mind what we're going to end up doing here. We're starting off at a height of 1.5 meters above the ground. Then we have a 16-meter diameter wheel, right? So that's 16, which means this is going to be 8. This is going to be 8. So really, if we're looking at it in terms of height off the ground, our axis should be what? What should the axis be? Yeah, so the axis is going to be 9.5. So when I said I agreed with you, I partially agreed with you. I shouldn't have said I agree with you. 1.5 is the height that we start at, but it's not the axis height, okay? The axis height is going to be right here at 9.5. That's going to be our C value, okay? And the reason why it's the axis, keep in mind, what's going to happen is I'll start graphing this for you just so you get an idea. I start at this point here, right? I get on at this point. Then after a certain amount of time, I go up to this point. Then after a certain amount of time, I go up to this point. A certain amount of time, I go back down, and then I go around once. Now we know that that should take 30 seconds, but that's going to model itself as a nice, pretty little wave like that. Okay? So this 1.5 is where we start, but the 1.5 is actually our min value. What's our max value going to be way up here? So the min is going to be 1.5. What's our max value going to be? Okay, good, Ashraf. 17.5, right? 16 plus 1.5, so 17.5. If you remember last week, we said we could define what our axis would be and what our amplitude would be based on the max and min. So if you remember, the amplitude is equal to the max minus the min all over 2. Max is 17.5 minus the min, which is 1.5 over 2. That's 16 over 2, which is 8. Coincidentally, that's also the radius of this Ferris wheel. So the amplitude is 8 here. The axis is the max plus the min over 2, or the average of the two. So we have 17.5 plus 1.5 all over 2, and that's going to give you 19, and then 19 divided by 2 is 9.5. Okay, so those two things become very important because the amplitude is A, and the axis is always C. Okay, so right now, what we basically have are two of those values. We can say y here is equal to the amplitude, which is 8 times the sine of k x minus h plus 9.5. All right. Now then the question becomes, how do we get k and how do we get h? K will be the easier one to do because we've already said that the period, remember from the last page, period was equal to 2 pi divided by k. Now the k value in this case is what we're looking for, so we can kind of switch those out. If we multiply by k, divide by the period, you get k here is equal to 2 pi divided by the period, which is also then true. Well, the period in this is that it takes 30 seconds per revolution. So 30 seconds for one cycle. So that's going to be our period. So we get k is equal to 2 pi over 30 seconds, which is pi by 15. So that kind of helps. So y then here equals 8 sine pi by 15 times x minus h plus 9.5. Okay, now would you say here we have the majority of this thing done? I think we have the majority of this thing done. But here's the question, and this is where we get into a little bit of trouble. It's this idea of our sine wave isn't going to match up with that. So h doesn't equal 0, and I'll show you why. If h equals 0, okay, I want to start with the sine wave, because really what we've done is at x equals 0, okay, so at x equals 0, remember, we've said that this height should be at what? This height should be at 1.5. And then it goes up to 17.5. What we have stated is that our sine wave should be starting down here. And then it goes to this point here at the axis, and then it goes back up here, and then back down here, and then back here. Okay. Oh, yuck. Okay, and then it'll go back up, and it'll just keep continuing on and on and on like this. So the difficult thing is here that our regular sine wave does not start like that. Our regular sine wave starts at 0, 0, but then goes up like this, right? So basically what we have is this piece right here. The point at which our sine wave usually starts right here actually corresponds to this point on the graph. So what we're really doing, we want to look for this point on our sine wave. Does that kind of make sense? So really what we need to do is take our sine wave and we need to shift it to the right a little bit. Okay, we need to shift our original sine wave a little bit so that we're talking about the point at 0 where they're at the bottom. Okay. So if we move this slightly, now I don't want you to think this has anything to do with the original question. This has to do with everything about our original sine wave. It does not have to do with the 30 seconds at all. When we're looking at our sine wave, what we want to do is get our initial value over on the x-axis. Okay, so we're going to shift our initial sine wave just a little bit. Okay, and the way we're going to do that, lost some stuff. So the way that we're going to do that in terms of shifting our sine wave is we need to know where the initial points are. Okay, so where those initial points are, remember we start at 0, 0, that's pi by 2 and 1, right? That's pi and 0. So this one over here at negative pi by 2 and negative 1, what we really want to be able to do is take this entire thing and shift it right so that this point right here, change the, so that this point right here goes to that point right there. And the whole purpose of doing that is to make sure that when the person is getting onto So when the person is getting onto the roller coaster, or sorry, not the roller coaster, the Ferris wheel, they're starting at the bottom. Right now, with a regular sine wave, they're starting at the axis. Okay, so we need to shift this over right, but we only need to shift it over right pi by 2, which means that our h value here is just going to be pi by 2. Okay, so this now is just going to be re-shifted. So 8 times the sine of pi by 15 x minus pi by 2 plus 9.5. All right. So really what we're doing then is all of that stuff that we looked at first, the amplitude, the max, the min, so the max and min, which gave us our amplitude and our axis, that helps us get our A value and our C value very easily. Then we have to look at the period to figure out what the K value is. And then from there, we have to look at what's called the phase shift. So the phase shift, the sine wave starts, so when you're looking at it at x equals 0, the sine wave starts at 0. And so we had to shift that a little bit. Now what's interesting about this is that we could have modeled the exact same thing with a cosine wave, and it been done much easier. Okay, so, but actually all of the other stuff would have stayed the exact same. Okay, but based on the starting position of cosine, watch this. I'm just going to erase some of these points. Okay, remember the starting position of cosine is not 0, 0. Starting position of cosine is up at positive 1. Right, so if we're looking at cos, so y equals cos x, we'd start up at the top and then go down and then come down again, then come up here and then go up there. Now, we could do this as a shift, but really, if we reflected this in the x-axis, then what we'd be doing is we'd actually be starting down here at -1 and going up like this. Okay? So that looks an awful lot like that diagram up there. So at least what this would help us do is show that we can actually model this in the exact same way, but the only difference would be that we would have to show a vertical reflection or a reflection in the x-axis, which would mean our initial value, or our amplitude would be 8 still, but we'd have to have that negative there. And then we would have no phase shift whatsoever. So it would just be, oh, sorry, I'm messing stuff up. It would just be this. It would take the shifting out of it completely, because we could just make it negative, flip the cosine function, and have it so that we start at the minimum, which is just like what the roller coaster is, or sorry, what that thing is doing. Not get it when you get H. I don't understand what that means.
How did you calculate that H equals P by 2? Pi by 2, sorry.
How did I get it that H is equal to pi by 2?
Yes.
Okay, give me a second to erase some stuff. Hang on though. Before we move on, does that actually make sense to everyone though? Like what I'm saying about how you can actually use a cos function instead of a sine function? Hopefully it does. Okay, so what I'll do then is I'll regraph the y, or sorry, the sine x function, and then I know you guys are antsy to get out of here, so I'll give you the what's it called? Okay, so normally the regular sine function, okay, as you should know, starts at 0, 0, goes up to the max. I'm going to use it in terms of maxes and mins. Okay, so it starts at the axis, goes up to the max, goes back down to the axis, goes down to the min, goes up to the axis again, right? So the sequence starts as axis, max, axis, min, axis. Does that kind of make sense what I'm saying here for y equals sine x? Yes? Okay, but on the graph that we're looking at that talks about our Ferris wheel, they don't get on at the axis, they get on at the min way down here. Okay, and then from the min, so when time equals 0, they should be at the minimum value on the graph. Then the next point they go to is the axis, then the max, then the axis, then the min, then the axis, then the max. Right? That's what this is showing. You start at the min, then go to the axis, then go to the max, then axis, then min. So what we have to do is we have to shift our graph, the y equals sine x, so that at x equals 0, they are at, so the y is equal to the min. Well, there's a couple ways you can do that, but the easiest way is to look at, okay, well, when was it at the min? Okay, it's at the min at negative pi by 2. Okay, so that means we would have to shift our entire graph right pi by 2 units. So, and then if we shift it right pi by 2, now this entire graph becomes, this point is here, this point is here, this point is, that point's there, this point's here, this point's here. And so that's what we end up having now, which is exactly what we want. So sine of x is the blue one, but y equals sine of x minus pi by 2 is this one where they start at the minimum value. And then it goes up through the axis. So if we have that starting point, then we can do those transformations of the horizontal compressions, the vertical stretch, the shift vertically, and then it will turn into that graph that we want that looks like the actual Ferris wheel. Okay?
Okay. Can H be a second? The unit can be seconds? Like, is it 30 divided by 4 second? The period divided by 4?
No. So the phase shift is based on the original sine function, but when you're putting in a value, the value you'd be putting in is x. So x would be in seconds. So if you graphed this, you could keep in mind, you could graph this just by using standard points, right? You could say, okay, when time is 0, I sub in 0 for this, what's my value? When time is, 1 second, 10 seconds, 15 seconds, what's my y value going to be? The problem is that you're shifting it based on the original sine function. So you have to do that in pi radians or degrees.
Okay. Thank you.
No problem. Okay, so I know that's that might be slightly, I don't know, I guess interesting for you. But the thing that I like about this is this last piece that I guess before I answered his question, is that you can model these with sine or cos, and all it's going to do is change what your A value is, either being positive or negative, or it's going to be your phase shift is going to be slightly different. Okay, so I'm just I'm gonna clear the page. I'm gonna mute myself for a second, and then I'm going to put in the some homework or some suggested homework for you. And if you have any questions, I'll stay on, but I won't be able to be on audio. I'll only be able to type in responses and use the whiteboard for about 10 minutes. And I'll give you the attendance form as well. Okay. Okay.
Sir, sorry, I missed the end there. Do we have a quiz next week? Oh, hello?
Yes. You are going to have a quiz next, or you mean Thursday, right?
Yeah, sorry, I meant Thursday.
Yes, you are going to have a quiz on Thursday. The quiz is going to be on everything to do with trig that we've done so far.
Everything was done so far?
Just in trig, though. So really, that's like basically you're talking about angle measurements. You're talking about the special case triangles and stating expressions. Like what are the primary trig ratios?
Okay. So none of the graphing, the sinusoidal, whatever they call them, sine function.
Yes, that included. Even tonight's stuff.
Oh, tonight's stuff isn't okay.
Yep. So graphing the primary trig ratios, those functions, graphing reciprocal trig functions could be on there, and then what we did tonight.
Okay.
Okay, so transformations. Now, the only things I'll give you transformations of are sine or cos, though.
And graphing reciprocal trig functions, that was done, I'm guessing, in last week's class, right?
Yes, it's just one over those. So if you know how to do reciprocal functions, then you know how to do reciprocal trig functions. It's just as long as you know how to graph the initial y equals sine x and y equals cos x.
Okay, perfect. Thank you.
Okay.